So in this video we are going deeper into our models of growth and decay. Right in the beginning of this term we started already with the exponential function, and we'll be refreshing our knowledge of our exponential growth and decay function, and then we will learn new things about them. And so this video is entirely just an overview, so I'll point at a few things here on the screen and then talk a little bit about the basic characteristics, and then in the next videos you will have different examples of exponential growth and exponential decay. So we are first focusing on the upper part, so this part on the left and this part on the right, in order to kind of refresh our memory, and then we'll focus on the newer items below that. So on the left side is an exponential growth function, and on the right side is an exponential decay function, and they both can be described by the function that we already know very well, f of x equals c times a to the x. That's this one here, and that's the same on both sides. Now, to refresh our memory, c is the initial value, so right in the beginning of when we start at time 0 is when we find our value c. Now, then we have our growth factor, a, so that's over here. Now here is where the two distinguish themselves, so it's actually in the a. So the c is the initial value no matter what, but then the a is greater than 1 for if it's exponential growth, and it is between 0 and 1 if it's exponential decay. Now a always has to be positive, that it means it's always greater than 0, and it cannot be 1, because then 1 to any power is just 1, so nothing changes. We also started to look at a as 1 plus r, and r in this case is our constant growth rate. And so I wrote it down here in two ways. So here we see a is 1 plus r for actually both. However, due to the nature of a, so if we solve this equation for r, then we get in both cases r equals a minus 1. However, when a is greater than 1, then a minus 1 is a positive number. So that means when we have exponential growth, then our constant growth rate will be positive. While when we have exponential decay, then our constant growth rate will be negative, because the number will be less than 1, so a minus 1 will be negative at the end. So that's a little refresher about our basic function f of x equals c times a to the x power. Now we're going to focus on figures 3 and 4 a little bit. So this part and this part for now. And we again have our same function as you see represented in the graph. They look exactly the same. However, this time we are writing them differently. And it's not just the letters that are different. At the end you can choose any letters you want, and you've already seen that sometimes c times a to the x power is written as a times b to the x power. So here also, where there's written an a or an n in figures 3 and 4, you could also take any other value, or sometimes for growth you choose n. That's very frequent because it sounds like number, right? N. And so you find all kinds of letters, but just it's easy for right now to distinguish the two a little bit. And so therefore, when it's exponential growth, we are having a function a of t, and when we have exponential decay, we call it n of t, just for this particular video. And then the basic setup is again very similar. with slight changes. So instead of our c, we say a sub 0. So a sub 0 is our initial value, or then in the exponential decay it will be n sub 0. And the 0, the little 0 at the bottom just denotes that that's the initial value. So that's very common in the sciences all throughout. When you have a variable and you put a sub 0, it's something to do with a beginning. And then for any other time, we then have our function a of t or n of t, and that denotes then whatever other time we will have at 1 second, 2 seconds, 3.5 seconds, whatever we need. And it's also to note in this case that we're choosing instead of xt simply because these models now that we are looking at come very much out of applications. So very applicable, and all of these growth models are usually growth or decay over time. So therefore our independent variable is usually time, and then we either have an amount maybe of a certain chemical that is decreasing in the body for medication, or a certain number of bacteria is growing, or any kind of populations. Usually we're talking about numbers, is n, or whatever other variables we have. Now then, what happens to our growth factor? Our growth factor is now looking slightly different, and it's expressed, so our basis is no longer a, but our basis is now e. And e is not changing, right? So instead of having a growth factor where the basis is basically changing in the exponential expression, it is now put in the exponent that changes, and that's that little k. And that little k we call the continuous growth rate, or the continuous decay rate if it's decay. The difference is now we no longer calling it the constant growth factor, and it's also not the constant growth rate. So the constant growth rate was in the basis. Now it's in the exponent, and that is denoted by the continuous growth rate. And that comes from the continuous interest that we just got to know in a few videos ago. And so from there comes that same idea that something is continuously happening. So if you have, for instance, a material, that is decaying, it's constantly doing it. Or if you have a large population of whatever species you have, there's a constant growth happening. And so that's kind of where that same idea that we had when we had finances, that we would continuously, so at every moment of life, calculate our interest. In the same way, here we are saying at any moment of life, growth is happening or decay is happening. And that brought about the idea to have it similarly expressed to the continuous interest rate. And there's another advantage to that, is that now that it's in the exponent, the k is very clearly greater than 0 if it's growth, and it's less than 0 when it's decay. So it's a little bit easier to kind of right away see, do you have growth, do you have decay? And that is also the reason that we use a lot the ln, because our basis is e, and we just then oftentimes, in order to solve for our time, or we also will be solving for our continuous growth rate, we need the ln in order to get to the exponent. Now at the very end, I want to notice one more important part in these considerations, and that is the idea of the doubling time and the half-life. especially the half-life is, let's start there, and that is specifically for radioactive substances. So radioactive substances basically, let's say, continuously decay at a certain factor. Let's say for the idea of this video right now, they're cut in half every time. Now if you take a certain material, anything you have, and you take it in half of it, and then you cut it again in half, and you cut it again in half, you always have something left over. Right? Take your pencil, for instance. You always have a little bit left that you again can cut in half. So you never kind of get zero. And so the question is, how fast or how slow is it decaying? You will soon see that the decay rates and the growth rates have very interesting numbers, and they don't really tell you how fast something is going. They have a lot of zeros usually in them, and are either really small or really big. And so the idea of a half-life is really helpful. That means that is the time that it takes for the quantity of the substance to be 1/2 of its original amount. And then in the same way, the doubling time, so we had that a little bit already with the finances, that it tells us how long does it take for a species, for instance, for a population to double. And we will see in the next video actually that it actually doesn't matter with what amount you start, that time is always the same. And so that is a very constant one that actually gives us more information. So we can easier see it in times, because we can say in seconds, we can say it in minutes, we can say it in years, in hundreds of years, and thousands of years. And so we have a broad spectrum of how we can make sense of these numbers better than with the actual rates. And so both those times are very, very useful in both population growth, as well as in any population considerations, as well as in radioactive substances that are used a lot, especially in medicine, but also in industry, and to know how long a radioactive material, for instance, will be effective, or how long you can expect to use it before you have to replace it with something new. So in the next video now, you start already seeing the example here at the bottom of the screen. We will get into an example and kind of calculate through a few things. And then there will be more examples in subsequent videos.